Have you ever just stepped outside, looked up at the night sky, and tried to truly wrap your head around the sheer, epic scale of our universe? It is this vast, incredibly dynamic expanse, and honestly, the fact that we can even begin to understand it represents one of the absolute greatest intellectual triumphs in human history. So welcome to this explainer. Today, we're going on a deeply intellectual, detailed journey into the math, the history, and the profound mysteries of the cosmos. We aren't just going to give you the surface-level summary of the Big Bang. No, we are going to look right under the hood. We'll be exploring the actual mathematical equations that dictate space and time, rewinding the cosmic clock to exact fractions of a second after the universe's birth, and confronting some wild modern anomalies that are challenging literally everything we thought we knew. Here's our roadmap for today. First, discovering the expanding universe. Then, the math of cosmic expansion. Next, the first 3 minutes. After that, relics of the early cosmos. And finally, the dark energy mystery. Let's dive right in. Section 1. Discovering the expanding universe. From a static illusion to a dynamic reality. So picture this. Up until the early 20th century, the scientific consensus was actually pretty straightforward. Everyone just assumed the universe was a static, fixed, and eternal place. But a massive paradigm shift was waiting just around the corner. Let's contrast two absolute titans of physics. Back in 1917, when Albert Einstein applied his brand new equations of general relativity to the universe as a whole, he ran into a glaring problem. The math showed the universe couldn't just sit there stably. Gravity would inevitably cause it to collapse in on itself. So, to force the universe to stay perfectly still, Einstein introduced a mathematical patch, a fix he called the cosmological constant. But then, fast forward to 1922. The Russian mathematician Alexander Friedman took those exact same equations and rigorously proved that if you assume the universe is homogeneous, a steady-state solution is fundamentally unstable. Friedman's math revealed that our reality must be dynamic. It had to be expanded. And you know what? Friedman's purely mathematical theory was spectacularly proven by real-world observation. In 1929, American astronomer Edwin Hubble was analyzing distant galaxies, and he discovered this incredible linear relationship between their distance from us and their recessional velocity. Simply put, the farther away a galaxy is, the faster it is moving away from us. The universe is uniformly expanding. Now, if we jump to modern times, the expansion rate calculated by the WMAP probe is an incredibly precise 70.4 kilometers per second for every megaparsec of distance. What does that actually mean? Well, to put that into perspective, for every 3.2 million light-years you look out into space, the fabric of the universe is expanding 70.4 kilometers per second faster. That specific number is literally the heartbeat of our cosmic expansion. Confronted with Hubble's undeniable telescope data, Einstein had to famously concede that trying to force a static universe with his cosmological constant was his greatest mistake, or as he called it in German, his 𝐿, essentially a donkey-like blunder. But that realization opened a profound new door in physics. Think about it. If the universe is expanding outward today, well, it must have been smaller yesterday. And the Belgian physicist Georges Lemaitre logically deduced that if you run the tape backward, at some finite time in the distant past, all the mass of the universe must have been concentrated into a single, unimaginably dense point. He called this the primeval atom. It was the brilliant conceptual birthplace of what we now call the Big Bang Theory. Which brings us to Section 2, the math of cosmic expansion, demystifying the equations of general relativity. To truly understand the cosmos, we really have to speak its language, and that language is Einstein's field equations. Let's break this down. On the left side of the equal sign, you've got the R and the G symbols. Those represent the actual geometry of spacetime, how it physically curves and bends. On the right side, the T represents the energy and matter contained within that space. This beautifully encapsulates the golden rule of general relativity. Matter tells space how to curve, and space tells matter how to move. And right there, nestled in the middle of the left side, is lambda. That is the infamous cosmological constant Einstein introduced to balance out gravity and artificially freeze the universe in place. Now, that directly feeds into the physical expansion of the universe through what's known as the Friedman acceleration equation. Derived straight from Einstein's foundation, it might look a little complex at first glance, but it tells an amazing story. The term on the left represents the acceleration of the cosmic scale factor over time. It basically shows us exactly how the energy density and the pressure of the universe physically pull against expansion via gravity. And check out that lambda term on the far right. It acts as a repulsive force, literally pushing the universe apart. This specific equation right here is the absolute bedrock we use for predicting both the past and the future size of our universe. Moving on to section 3, the first 3 minutes. Rewinding the clock to the quantum realm. Okay, so now that we have the math of expansion, let's use it to rewind time. We are shifting from the massive macro-scale mathematics of galaxies moving apart all the way down to the microscopic quantum reality of the universe's explosive birth. If you push Friedman's equations all the way back to the very beginning, you eventually hit a wall. The math breaks. We call this the initial singularity. This is an environment so extreme, with temperatures hitting a mind-boggling 10 to the 32 degrees Celsius, that our current understanding of physics actually falls apart. At this infinitesimal point, the characteristic scale length of the entire universe was just 1.6 times 10 to the negative 35 meters. The electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity, they weren't separate. They were unified as one single superforce. Even the very concept of a physical particle ceases to exist under these conditions. To fully understand what happened here, humanity is literally waiting on a complete theory of quantum gravity, a mathematical framework that can somehow marry the physics of the incredibly massive with the unimaginably microscopic. Then, at just 10 to the negative 37 seconds after the Big Bang, that's a decimal point, 36 zeros and a 1, something miraculous happened. Cosmic inflation. The universe expanded exponentially, causing temperatures to drop drastically. This hyper-fast expansion solved what physicists call the flatness problem, perfectly balancing the density of matter to create a geometrically flat universe. But here is the most mind-bending part of the whole thing. Because of Heisenberg's uncertainty principle, there were tiny, microscopic quantum fluctuations in energy going on. Inflation happens so incredibly fast that it literally frozen in these quantum ripples, stretching them out to macroscopic sizes. Think about that. Those microscopic quantum jitters became the gravitational seeds that would eventually pull matter together and grow into the massive galaxy clusters we observe today. The really crucial takeaway here is just how highly organized this initial chaos actually was. As the universe expanded, it naturally cooled, which allowed those fundamental forces to finally separate, almost like ice crystallizing out of liquid water. By 10 to the negative 6 seconds, quarks and gluons finally bound together to form the very first protons and neutrons, but it was an absolute war zone. At roughly 1 second in, electrons and their antimatter counterparts, positrons, engage in this massive matter-antimatter annihilation. Fortunately for us, there was a tiny asymmetry, a very slight excess of normal matter. Only about 1 in 100 million matter particles actually survived that annihilation phase. You, me, the Earth, and all the stars in the night sky. We are entirely made of those extremely rare survivors. And that brings us to a spectacularly detailed phase of early cosmic history called Big Bang Nucleosynthesis, or BBN for short. Within the first few minutes, the universe's overall temperature finally cooled to about 1 billion Kelvin. At this very precise thermal threshold, protons and neutrons could finally combine and stick together without being immediately blasted apart by high-energy radiation. They started forming the very first light nuclei. Now, because this process relies on deeply understood, rigorously tested standard model particle physics, BBN is widely considered by cosmologists to be the deepest, most reliable probe we have into the conditions of the early universe. And the physical evidence for this is mathematically stunning. Based solely on the temperature and density of the early universe, BBN theory predicts exact primordial abundances for the light elements. For instance, the math predicts that helium-4 should make up exactly a 0.245 mass fraction of the universe. So what happens when modern astronomers point their telescopes at distant, unpolluted gas clouds, areas totally untouched by stellar evolution? They find an exact match of roughly 24.5% helium-4. And this accuracy spans 9 orders of magnitude, all the way down to tiny, microscopic traces of lithium-7. It is an absolutely monumental validation of the hot Big Bang cosmological model. All right, let's look at Section 4, Relics of the Early Cosmos, the Echo of the Big Bang. So we've talked about the math, and we've walked through the subatomic synthesis, but how do we actually see the physical echo of the Big Bang today? Well, first, let's look at the age of the universe, 13.787 billion years. I really want to stress that this number is not just a wild guess. It is a highly rigorous calculation derived from meticulously measuring those current expansion rates we discussed and analyzing the oldest observable relics in existence. And the absolute most famous of these relics was created exactly 380,000 years after the Big Bang. See, before this specific time, the universe was basically a super hot, opaque plasma.
Photons of light couldn't travel freely at all because they kept violently bouncing off loose electrons. It was like a thick fog. But as the universe expanded and cooled enough, electrons finally bound to nuclei to form the first neutral atoms in a process we call recombination. Suddenly, almost like a switch flipping, the fog lifted. The universe became entirely transparent. That very first burst of light, the last scattered photons from that era, has been traveling freely through the vacuum of space ever since. We finally discovered it in 1964, and we call it the cosmic microwave background. It is quite literally the afterglow of creation. Which brings us to our final topic, Section 5, the dark energy mystery, accelerating into the future.
Up to this point, we've built a remarkably pristine historical picture, right? But modern observations have thrown a massive, unexpected wrench into our models. For decades, cosmologists safely assumed that the universe's expansion was naturally slowing down due to the collective gravitational pull of all the matter inside it. But in the late 1990s, we discovered the exact opposite was happening. The expansion isn't slowing down at all, it is actively accelerating. The enigmatic force driving this outward acceleration is what we call dark energy. And here is the profound irony of the whole situation. The absolute prime mathematical candidate used to model this unknown vacuum energy is none other than lambda. Yes, the cosmological constant. Einstein's self-proclaimed greatest mistake has literally returned from the grave to completely dominate modern astrophysics. To try and actually understand this, scientists have had to build massive global collaborative projects like the Dark Energy Spectroscopic Instrument, or DESI for short. This incredible collaboration recently released a mind-blowing analysis mapping nearly 15 million galaxies and quasars in 3D. Think about the scale of that. They've essentially traced 11 billion years of our cosmic history to see exactly how dark energy has influenced the universe's expansion over time. And their initial findings, they are sending massive shockwaves through the entire physics community. Here's the twist. When you combine this brand new DSI data with our older studies of the cosmic microwave background and supernova, the standard model of cosmology actually struggles to fit perfectly. The new data strongly hints that dark energy might not be a static cosmological constant after all. Instead, it seems its influence could actually be evolving, genuinely changing its physical strength over time. This is an incredibly fertile, thrilling ground for theoretical physicists today. It means our understanding of the universe's fundamental ingredients isn't a closed book. It is still actively being written. Which really leaves us with this final, incredibly profound question. If dark energy is actively evolving over time, what is the ultimate fate of our universe? Will the cosmos just expand forever into a cold, dark void? Will it eventually rip itself and all matter apart? Or will an evolving dark energy somehow reverse course entirely and pull everything back together in a massive crunch? We started today with Einstein's math. We traveled through the unimaginable subatomic fires of the Big Bang, but as you can clearly see, the cosmos still holds breathtaking secrets. Thank you for joining me in this explainer. Keep your curiosity alive, and as always, keep looking up.